So today we're going to look at the work-energy theorem. Recall from the previous lesson we talked about conservation of energy and said that energy cannot be created or destroyed, only changed. So this is really one of the most powerful, if not the most powerful law in physics. So let's look at this in action. Let's say, for example, I'm here and I'm going to push a box. Actually, let's just make it a cart so we can say there's no friction. So I'm going to apply a force on this, let's say over some distance. So clearly the box is going to, or the cart's going to start moving, right? So I'm doing work on this cart. I'm going to start pushing it. I'm going to let it start moving. Okay? Let's say that I do 100 joules of work. So the question is, once I let go, I do 100 joules of work over this distance. Once I let go, where is that energy? Where did it go? Can't be destroyed. Where is it? Well, we would say that energy is now contained within the motion of the moving cart. How much energy? Well, 100 joules. The energy, the exact amount of energy that I started with. So this now has 100 joules of energy. And how do we know it has energy? Remember, something has energy if it can do work. So for example, if I put a ball right here, can this cart apply a force over a distance on the ball? Well, clearly yes. And however much work it does, let's say it does 5 joules of work on the ball, well then this cart now will have 95 joules. It will give up 5 of its joules of energy to the ball, and so it has 95 and the ball now has 5. Okay, so maybe a bigger question then is, well, where did I get this 100 joules to do the work in the first place? Well, I got that from, well, food, right? So I ate some food. Food goes in here, and I basically changed that food into this work that I'm now able to do. Well, where did that food get its energy? Well, that food must have got its energy. Well, it depends what I ate. Let's say I ate some broccoli. Well, if I ate 100 joules of broccoli, broccoli got its energy from the sun, right? So the sun came in, gave its radiant energy to the broccoli, I ate it, and then I pushed the cart, and then the cart hit the ball, and so forth. Well, where did the sun get its light energy? Well, it got it from its nuclear energy, because the sun itself had its nuclear energy, and that's where the light comes from. So anyway, the whole concept is this 100 joules of nuclear energy eventually turned into this 100 joules of the moving car. And we didn't lose any. All that happened didn't just get destroyed. All that happened is we changed through these different forms. Okay, so let's kind of derive the equation for this. Again, this conservation of energy law, we could kind of simplify this into an equation, and it's probably the simplest but yet most powerful equation in physics. And we can say E initial equals E final. In other words, the energy that I start with has to equal the energy that I end with. So let's do this in mathematical form. So in this case, if we go E initial equals E final, the energy I started with was, well, the work. And the energy that I ended with is this energy of motion. And this energy of motion we're going to call kinetic energy. Kinetic energy. You can see that word kinetic meaning motion. So this energy of motion we're going to call kinetic energy. So the work I started with is going to turn into kinetic. And actually, let's be a little bit more specific. This is going to be the change in kinetic energy. How much the kinetic energy is changing. For example, let's say this object had 100 joules to start with. All right, and I'm just going to push it more. So I'm going to push it with the force over a distance. I'm going to speed it up. I'm going to add another 100 joules to it. Well, now the cart is going to have 200 joules of energy. Started with 100, and then I gave it another 100, and now has 200. So the change, though, is still equal to whatever work I imparted onto it. Okay, so let's go ahead and derive this. If you remember, our equation for work is force parallel to the distance. If you recall our huge equation from the last unit, F equals ma. Let's make that substitution. We can write this as MAD, or MAD. Let's recall from 2 units ago, our kinematics equations, Vf squared equals Vo squared plus 2AD. And if I rearrange this to get my AD, I'm going to get Vf squared minus Vo squared equals AD, and let's divide that by 2. Okay, and let's get some more paper. So we're going to go ahead and substitute that AD into here. Let's see what we end up with. So we have work equals m. We'll make this substitution right here. Vf squared minus Vo squared over 2. That's a substitution for AD. And we usually rearrange this into another form. We'll pull out the 2 and let's just split this up here. We're going to get 1/2 mv final squared minus 1/2 mv initial squared. So this is what we call the work energy theorem here. And we're going to define this term. Notice we have the same exact term. One is a final, one is initial. We're going to call that our kinetic energy equation, 1/2 mv squared. So notice again what we're left with is that concept that we talked about just initially, which is our work is equal to this kinetic energy final minus this is kinetic energy initial, Ke final minus Ke initial, which is equal to the change in kinetic energy. Alright, one quick word about kinetic energy. Notice what it's proportional to the mass. So for example, if we were to double the mass here of the object, we would double the kinetic energy that it has. The other factor is the velocity. Now notice the velocity is more important than the mass. For example, if we were to double the velocity, then we would 2 squared times the kinetic energy, or quadruple the amount of kinetic energy we had. Okay, so here we go. This is our work energy theorem. And it's really just a conservation of energy concept. And I'm now going to have you do a couple of examples. And as usual, I would encourage you to try these examples first and then watch the solution.